Hi everyone, my name is Neha Kardam and this is the sixth lecture on electronic communications. In this lecture, we will learn about phase-locked loop theory and frequency synthesis. Let's first learn about a voltage-controlled oscillator. This voltage-controlled oscillator is the part of a phase-locked loop, and this states that it is an oscillator whose frequency can be controlled by the external voltage. So as you can see here, the control voltage is given to the VCO, where VCO stands for voltage controlled oscillator, and with the help of this control voltage, the output frequency can be changed. Now if we talk about the conventional oscillator, the frequency of the oscillator can be selected by the passive components like resistors, capacitors, and inductor. And by changing the values of those passive components, it is possible to change the oscillation frequencies. So in conventional oscillator, if we want to change the frequency, then we need either a variable capacitor or a variable resistors. And manually, we need to tune these components to change the frequency. Whereas in a voltage control oscillator, it also needs passive components for the frequency generation. But with the given set of passive components, just by changing the control voltage or tuning voltage, it is possible to change the tuning frequency. So these VCOs, they are much convenient to tune than compared to the conventional oscillators. And in fact, if we want to tune the voltage controlled oscillators using the microcontroller, then also it is possible. So let's see that in the next slide. So here you see that we have the this digital to analog converter, and then we have this microcontroller attached to this DAC, and from here we are controlling the or we are providing the controlled voltage to the voltage controlled oscillator, and at the output we have the change frequency with respect to the change in the controlled voltage. So commercially available these VCOs, they can work from a few hertz to around tens of gigahertz, and because of that they are used widely in the communications. Now moving on to the next slide. Here in this slide we see different types of voltage controlled oscillators. Under that we have harmonic oscillator and relaxation oscillator. Under harmonic oscillator we have RC oscillator, LC oscillator, crystal oscillator. All these oscillators generates a sinusoidal signal, whereas this relaxation oscillator, it generates either square, triangular, or the sawtooth signals. Commercially, both types of oscillators are available in the IC packages. Now let's see theoretically the harmonic oscillator, and this can be converted into a voltage controlled oscillator. For example, instead of tuning the R and resistance and the capacitor manually, if any of them is replaced by the voltage controlled element, then they can be used as a voltage controlled oscillator. As you can see in this example, we have this LC tank circuit, which is your Colpitts oscillator, and this is replaced by the capacitor. Here are replaced by these diodes. Here these diodes acts as a variable capacitor. As we change the applied reverse bias voltage across these diodes, you see, then the capacitance of the diode will also change, and by changing these reverse bias voltage, we can change the oscillator frequency. So as you can see here, as the reverse voltage increases, the capacitance also changes. Now for any type of LC or RC oscillator, the frequency you can see here is proportional to 1 by under root RC, and this is in the case of RC oscillator. In case of LC oscillator, frequency is directly proportional to 1 by under root LC. So in both of these we see that the frequency is proportional to 1 by under root C. And in VCOs, the varactor diode, as we increase, as you saw that we increase the frequency, as we increase the voltage, then the capacitance of the diode will reduce. So you can see here, if the voltage is increased here, then at that point the capacitor value will be small, whereas if the reverse voltage is small, then at that point the capacitance is higher. Now moving on to the next slide. In this slide you see the curve between frequency and control voltage, and you see that this F0 is the nominal frequency and this V0 is the nominal voltage. And as we increase the control voltage, the frequency of the oscillation you see will also increase. And if the control voltage is also varying with the time, then mathematically the frequency of the oscillation can be given by this expression you see here, where F0 is the nominal frequency and K is the tuning gain, and VC basically stands for control voltage. This tuning gain can be defined as amount as by what amount the frequency of the oscillation will change when we change the control voltage by 1 volt, and the unit of this tuning gain is hertz per volts. Now we have the relaxation oscillator. And this can also work as a voltage controlled oscillator. So in relaxation oscillator, by changing the charging current of this capacitor, it is possible to tune the frequency. So like in this type of oscillator, the charging current is proportional to the tuning voltage. Means by controlling this tuning voltage, we can change the rate at which this capacitor basically charges. And now here in this figure you see a Schmitt trigger circuit where the voltage across the capacitor, the voltage which will appear here across the capacitor, is compared with the V reference voltage. And when this capacitor voltage reaches the V reference voltage, then the output of the Schmitt trigger will change. And let's see that in the next slide. So here you see that the output voltage waveform is given, and this waveform represents the VC, which is the capacitor voltage here. So with this change, the polarity of the reference when this VC will basically when this VC reaches the V reference, then what will happen? There will be a change in the polarity of the V reference as well as in the direction in which this capacitor charges. So the polarity will change when this reaches to the V reference frequency. And you can see that how this VC controlled capacitor voltage is triangular, and output voltage how it is square wave. And we know that out of Schmitt trigger we get a voltage output like this, and by changing this this output voltage will also change. In IC 566, if you look that IC, then you will see that it also works in a similar fashion the way this works. And in fact, in the 555 timer also, it with little tweak you can also make it work as a voltage controlled oscillator. Now next we are going to see the important specifications of voltage controlled oscillator, and under that we have these 4 important points. First is the tuning range, Second is the tuning gain and or tuning sensitivity. Third is supply pushing and loading pulling. And the fourth is the phase noise. So let's discuss each of these. Tuning range, it is defined as the range over which the frequency of the voltage controlled oscillator can be tuned. If you see the datasheet, the manufacturer provides the range of the control voltage and the corresponding tuning range. For example, for VCO, control voltage is, let's say it's varies from 0.5 volts to 20 volts. Then the frequency can be changed from 40 megahertz to 80 megahertz. So here, this range you see is your tuning range. So as you can see here on the right side, the graph, as the voltage range is defined, and corresponding to that you have the tuning range. Next is tuning sensitivity, and tuning sensitivity is also called tuning gain, and it can be defined as by what amount the frequency of the voltage controlled oscillator can be changed when we change the control voltage by 1 volts, and it is defined in terms of hertz per volts. So let's say if your VCO has a tuning gain where this K is basically your tuning gain, and it has a value of 2 megahertz per volts, then we can say when voltage is changed by 1 volts, then the frequency of the oscillator will change by 2 megahertz. This tuning sensitivity may be constant over the entire tuning range, and it may vary with the control voltage. So as you can see here, this graph is given of a tuning sensitivity, and so here this represents your K, and this represents your tuning voltage, and you see how the graph is changing with respect to the tuning gain. So if you look for the datasheet, then you will see that they specify the typical range of the tuning gain instead of the specific value. For example, tuning gain varies from 2 megahertz per volts to 4 megahertz per volts, and it may vary for different devices. Now next we have supply pushing, and it is the supply pushing basically defines as the change in the output frequency with the change in the supply voltage. So ideally for a VCO, if supply changes, then there should not be any change in the output frequency. But practically output frequency does changes with supply voltage. So the change in frequency due to this supply voltage is known as the supply pushing, and the unit of supply pushing is also in hertz per volts. And this supply pushing, this can be minimized by using the regulated power supplies, or an oscillator circuit with high Q factor can be used. Now next we have the load pulling, and it says if there is any change in the output, any change in the load, then it should not affect the output frequency. But the output frequency does changes if the load changes, and that is called your load pulling. And in the data sheet, if you look for load pulling, it defines it as a maximum deviation from the nominal frequency. Now next we have the phase noise, and phase noise, it basically represents the random fluctuations in the phase of the output waveform, and this is due to the noise. And the noise levels, you can see here, these represents the noise, and these noise levels are particularly important when the VCOs are used for modulation and demodulation in the communication system. So here you see this is a weak signal, and these are the two noises we have. And weak carrier signal, this got suppressed by the phase noise of the strong carrier signal. So this phase noise is basically measured with respect to the power, and it is measured at a certain offset of the carrier frequency. So if the carrier frequency, is here, if the carrier frequency, then the phase noise at that point will come out to be here. It basically offset from a value of FC plus delta F, and that is your noise power. And if you look for the data sheet, then this phase noise is basically represented as different offset from the FC, and the unit of this phase noise is dB per hertz. Now next we are going to see the applications of phase locked loop. So here you see some of the application. The first is it can be used in synchronization and demodulation circuits. For example, in the frequency modulation, FM demodulation or AM demodulation, and in the frequency shift keying, they are commonly used. And then you have this recovery clock, which is the second application where it can be used. So when we want to recover the clock from the incoming bit stream, then with the help of PLL, it can be possible to generate the clock. And third is the noise and jitter reduction. It can be used in that case. And fourth is frequency synthesizers, as well as it can be used in tone generation. So in this, it is possible to generate output frequency in terms of input frequency. We will see that later on in this lecture. And then these are also used in microprocessor. So you can use clock multiplier and clock distributor. Now we see here is the input signal or the reference signal going into the phase lock loop, and at the output we see here a waveform. And at these two pictures basically shows the phase difference between the two signals. So first, let's understand what do we mean by phase difference. So here in this picture, you see these two signals have the same they have the same frequency, but they have the constant phase difference. Whereas if you see the two waves here in this right picture, you see the two waveforms, they start at the same time, but they are of different frequency. You can see how different they are. This is different and the frequency of this is different. In this case, the phase difference is continuously changing continuously changing with time. So in the phase lock loop the system basically synchronize the output signal with the input signal in the phase as well as in the frequency, and that is what we want to achieve. Now here, as we discussed earlier in the VCO, when the control voltage changes, then the frequency also changes. So whenever the loop is just turned on, then the VCO runs at the center frequency, and this frequency is also known as the free running frequency. Now the phase detector basically compares the input or the reference signal with the oscillator frequency, and based on that it generates the error signal, which is called your ET. Now this error signal is passed through the low pass filter, and the low pass filter generates the error voltage based on the error signal. And based on the error voltage, the VCO, voltage controlled oscillator, either increases or reduces the oscillator frequency until the oscillator frequency locks the input frequency. And under lock condition, there may be no phase difference, or we can say that constant phase difference should the two waveforms should have. So this is the condition of under lock condition. F naught is equals to Fn, where this F naught is actually this output frequency, and Fn here is the reference signal or the input signal, and the phase difference is 0, or we can say constant. So in this waveform you see it has a constant phase difference. Now what will happen if under no lock condition? Then in that case, you see here we have a capture range, and capture range is the range of the input frequencies around the voltage controlled oscillator center frequency, onto which the loop can lock when starting from the unlock condition. So under the no lock condition, the PLL can acquire the lock only if the input signal is within the capture range of the PLL, which means whenever the input signal is within the capture range, then the voltage controlled oscillator can lock to the input signal. Now moving on to the next slide. So here we're going to learn about the lock range, and it says it is defined as the range of the input frequencies over which the loop remains in the lock condition once it has captured the input signal. So this is another important specification of the PLL is the lock range. Now let's say the voltage controlled oscillator is already locked to the input frequency F, which you see here. Now if the input frequency changes, then the VCO will follow the input frequency. So you see that this pink arrow shows the new frequency, and the VCO, the frequency of the VCO will try to follow this, and provided that the input frequency is within the lock range. And so the lock range here is F minimum and F max. So under this is our lock range. So if the new signal is under this range, then our the VCO frequency will try to follow this and creates a 0 phase difference. But if the input frequency here in this example at the bottom picture you see, but if the input frequency goes out of the lock range, so you see that this new input frequency has gone out of the range, then the VCO starts running at the VCO frequency. You see F will starts running at the free frequency, and it won't be able to lock to the input frequency until the input frequency is within the captured range of the PLL. Now next is the phase detector, and it says the phase detector is the decision maker that compares the VCO frequency to that of the reference. So in the frequency domain, we see that this summation has two frequency. This is the first frequency, and this is the second frequency. Then at the output we will have the sum of these frequencies and the difference of these frequency is taken. So here these high frequency component which you see F1 plus F2 can be eliminated using the low pass filter, while while this difference between the two frequency contains the phase difference, and when this signal is passed through the low pass filter, then it provides the required error voltage for the voltage controlled oscillator. So using this error voltage, it is possible to log the voltage controlled oscillator to the input frequency. And at radio frequency applications, we see the balance mixture is basically used as a phase detector, while for the digital signals we can use XOR gate or phase frequency detector. So next we are going to see XOR gate, one of the digital phase detector we can use. So this is the XOR gate, and the output of the XOR gate will be high when the two inputs are different. That means whenever the two input signals are identical, then there is no phase difference between the two signals. Then ideally the output of the XOR gate should be 0. Now let's say at 0 phase shift, when V1 and V2 are given, which means when they are identical to each other, then we know that the output phase difference should be 0. But actually if you see here, you will find that some spikes can be seen at the transitions. So if we take the average of these phase difference signal, then it will approximately will come out to be equal to 0. Now what will happen if we have 90-degree phase shift? So if we have 90-degree phase shift, then your output signal will come out to be, phase difference signal will come out to be like this. And if we take the average of this phase difference signal, then we get the output voltage, which is basically, for this case, is half of the peak value. Now what will happen at 180-degree phase difference? So you see that our V1 waveform is like this, and now we see a 180-degree phase difference when you compare to this. And whenever the phase difference between the two signal is 180 degree, then the output will be maximum, and ideally it should be high for all the time. But actually there will be some spike at the transitions. So if we take the average of this output waveform, then it will be the maximum value. That means as the phase difference between the two signal increases, then the average value of the output waveform will also increase. So you can compare these two signals with the waveform, and then you will see that what output voltage will come out, and then you will have a better idea. Now here this is the plot of the phase difference and the average output voltage of the low pass filter. So you can see that the phase difference between the two signals increases from 0 to 180 degree, and then the average output voltage will also increase linearly. So you see this linear curve between the phase difference and the average output voltage. This means that the phase detector is the linear phase detector, but the phase relationship is linear only for 0 to 180 degree. Now ideally the phase detector should provide the linear phase relationship even after 180 degree, which means from 0 to 360 degree. But in XOR phase detector, as the phase difference increases beyond this 180 degree, then the average output voltage will start reducing. Moreover, it is difficult to identify which signal is actually leading or lagging. For example, irrespective of input signal V1, whether V1 is leading or lagging the V2 by 90 degree, we get the same output waveform. And apart from that, the XOR gate to work as a linear phase detector, both signals should have approximately 50% of the duty cycle. And whenever the two signals are operating at a different frequencies, then it is quite possible that the loop can get locked at the harmonic frequency. So there are some problems with the XOR gate phase detector, and these problems can be eliminated by using the phase frequency detector. Now next is the PLL loop states, and the PLL may be in one of the three possible states depending upon the inputs provided. The first is the free running state, second is the capture range, third is the lock range. You know that free running stage, under this condition there is nothing for the phase detector to compare the voltage controlled oscillator output frequency with. And in this state the VCO runs freely at its own natural frequency. And we can quickly read this also. No input signal is present at the reference input of the loop. The VCO tends to operate at the free run frequency around the middle of the PLL's operating range. Next is the capture range. So it says the PLL has just been supplied with a reference signal, but it hasn't acquired lock yet. It's trying to catch up. If the input signal isn't within the capture range, the PLL will remain stuck in this state. So in this the capture condition, normally it doesn't last for very long, and as the PLL immediately tries to get locked onto the input frequency, and the PLL it cannot lock onto all the frequencies. Only a certain range of frequencies within the capture range can be acquired if the PLL is initially in the free running state. And also this free running frequency is mainly in the middle of the capture range. Now next is the lock range, and it says the PLL has completely acquired the reference signal and the VCO frequency is exactly equal to the reference. As long as the signal stays within the lock range, the PLL will follow. So this lock range is the desired state, and in this state the PLL has basically successfully passed through the capture phase, and it has its VCO locked onto the input frequency, reference frequency. Now this slide talks about the PLL frequency synthesis, and if you compare the block diagram of the PLL with this one, then the only difference which you see is here. Here this extra block is added, and this says divide by n. So whatever the signal output is coming out of this VCO, it will be divided by this n factor, and then output of this signal will be sent to the phase detector, and here this value will be compared with the reference value. Let's read this. By inserting a frequency divider, which is this, into the feedback loop of the PLL, we change the frequency of the signal the phase detector sees. Since the phase detector obeys Finlay's law, the loop restabilizes but a new frequency. So here this Finlay's law for phase detector, it says that if the two inputs of a phase detector are not at exactly the same frequency, then the phase detector output will be either in the positive or a negative saturation. So we have already seen that, but now we know that it is based on Finlay's law. So here let's read this more. At test point E, which is here, will remain at the same frequency as the test point D due to the closed loop correction made by the phase detector. However, for this to be true, test point C, which is here, the VCO output will have to be n times the reference frequency. So it's saying that if you want if you want to remove the error, or if you want to remove the error, then this point must be equal to this point, which is going into the phase detector element. Then the signal passing from here and at the test point C, it should be multiplied with n. So when the signal, let's say if the signal is x, which is entering here, and here you will have x multiplied by n, which is xn, and that xn will enter here, and that xn will be divided by n. So we will have this x signal over here, and let's imagine that x signal is same going from here. So we will have these two signals which are same in frequency, and they are of same values. So here we found that by modifying the feedback portion of the loop, we can get the loop to produce new frequencies. We saw that here, and a frequency divider, this circuit is dividing an incoming frequency by some chooser number, and this chooser number can be any depending upon your circuit conditions. And these frequency dividers are really nothing more than the digital counter. If you get in detail, then you will get to know that. And the addition of the divider within the feedback portion of the loop changes the signal that the phase detector basically sees at this point. Now here is an example given, and it says if the reference frequency is 10 kilohertz, which means the signal is going from here to the phase detector, and it is of 10 kilohertz, and n is given, which is 76, then it says what will be the frequencies at test point E, which is here, and C. What value of n is needed to get an output frequency of 1320 kilohertz? Can this loop synthesize 765 kilohertz? Why or why not? So you can work on this problem, and since you know the principle, you can easily find out the answer of these questions. Now the next is a practical PLL synthesizer, and you see how it is different from the previous block diagram of the PLL synthesizer. In this one, we have extra components added over here, which is a master oscillator, and here you see divide by R, and a microprocessor or a microcontroller module here, block here. Let's first read this. A practical PLL synthesizers usually has a crystal oscillator providing the reference, so it needs a reference divider to reduce the crystal's frequency down to an appropriate value. Both the reference and the loop dividers are programmable and interface to a microcontroller, which takes commands from the end user and in turn controls the reference and loop dividers to put the loop on the correct frequency. So here the most PLL synthesizers, they require a relatively low yet stable reference frequency, and to have a stable reference frequency, what we can do, we can have a high frequency crystal oscillator, and that crystal oscillator can be used, and these crystal oscillator, they are also called this master oscillator, and it divides its frequency down digitally until the desired reference frequency is obtained. And this oscillator is usually in the 10 megahertz to 20 megahertz range. Here the frequency divider's job is to bring the master oscillator's frequency down to a proper value for the PLL reference input, and the reference divider is nothing more than another programmable divider. And here you see the microprocessor. It basically used to issue the commands to the various part of the programmable logic to the various parts of the phase loop locked system by sending digital values to each of the PLL registers. For example, here these registers are this one and this one. So here you see the PLL shown here has two stages that must be programmed by the software, and which is this N register and the R register, and the software basically controls all of these actions from here. Now next is the summary. So I'll just quickly read the summary, and it says PLL is a closed loop self-correcting system. The phase detector obeys Finlay's law. If its inputs are not at exactly the same frequency, its output will be in either positive or a negative saturation. Because of this, a locked PLL has zero frequency difference between its two VCO inputs. A PLL can be in free run, capture, or locked mode. Depending on the inputs provided, capture is normally short-lived and locked is the desired outcome. The frequency divider can be inserted into the feedback loop of a PLL, and this causes the output of the VCO to increase by the same factor n as the divider, and this is called the direct frequency synthesis. And lastly, it says a practical PLL synthesizer is computer driven and employs programmable dividers for both the reference and loop dividers. So this is the end of the lecture. Thank you so much for watching it.